Hi everyone. We're going to be talking a little bit today about solutions, and I'm not really talking about like solutions to a problem, leading to success or anything like that, like we have on this first graphic here. But really, instead, we're going to talk about chemistry solutions and what that actually means and some of the vocabulary that's kind of associated with it. If we're going to talk about solutions, we need to all kind of be speaking the same language, so to speak. One thing I would recommend you have handy as we go through some of these terms is this note sheet, which will be included in the assignment. So what I would recommend is having this handy, because we're going to talk about these different terms. I've highlighted in blue the ones that are in this particular lesson, and you should be able to fill the rest of this out kind of as we go through the unit. So let's start off by answering a couple of questions. You probably heard the term mixture. Well, we'll first start off by looking at what is a mixture, and then there's two types of mixtures that I think we've mentioned some of these vocabulary words, heterogeneous and homogeneous. So we'll revisit that and think about how that applies to mixtures. So the first question, what is a mixture? Well, really a mixture is when we just take two or more pure substances and we combine them. All right, and at any point throughout the video, if you need more time, feel free to hit pause. Again, add some of these vocabulary terms to that note sheet. That'll kind of act like your master sheet when it comes to, say, quizzes or tests. So let's define this a little bit further. So what is a heterogeneous mixture? Well, if we break that word down, hetero means different, all right? So it's going to look non-uniform, or it's going to look different. We can actually pick out the pieces. We could pick out the M&Ms, we could pick out the peanuts, we could pick out the walnuts, we could pick out the noodles, right, in our chicken noodle soup. So this is a mixture of different substances, but you'll notice that it doesn't look the same all the way throughout, because those particles are actually large enough that we can actually see those, and either under a microscope or sometimes even just with the naked eye we can see that this mixture is non-uniform. So let's compare that to a homogeneous mixture. So a homogeneous, homo means same, so it's going to look the same all the way throughout. So in this case, the particles are super small. They're molecule size. So we can't even see them with a microscope. They're so small. And so in this case, here's our Kool-Aid, or in this case lemonade. It looks uniform. It looks the same all the way throughout. Mini quiz time. What do you think? Here we have a picture of honey. Is that honey homogeneous or heterogeneous? Hopefully you're thinking, well, that's homogeneous. Look, it looks the same all the way throughout. How about our coffee? Is our coffee homogeneous or heterogeneous? Well, our coffee, again, looks the same all the way throughout, so that's going to be homogeneous. Lastly, how about our chocolate chip cookies? We could pick out the chocolate chips, right? We see the dough here. So in that case, that mixture is, in fact, heterogeneous. It doesn't look the same all the way throughout. What about our milk in the background? We're going to come back to that. Milk is actually a special type of substance, and we'll revisit that in a second. Hopefully, at this point, you would say homogeneous, just because it does look the same all the way throughout. So with the next couple of terms that we're going to talk about, I always like to reference Goldilocks and the Three Bears. And if you're not familiar with this story, now that you're older, it's kind of a disturbing story. I mean, this little girl, Goldilocks, literally breaks and enters into these three bears' houses, and then she's sitting in their chairs, eating their soup, sleeping in their beds. It's really kind of a weird story. But the kind of moral of the story is that there's a small bed or a small chair that's usually too small. There's the big bed, big chair that's too big, and then she ends up finding a bed or finding a chair that fits just right. So we're going to kind of relate to that story here as we talk about these next terms. So our next term that we want to talk about is a suspension. So this is a heterogeneous mixture. It looks different all the way throughout. But it can be temporarily homogeneous. So if we mix it up, for example, this is maybe some maybe some pond water, that we get some of the clay particles kind of mixed up, right? If we let that sit for a while, eventually those clay particles, some of that dirt and soot will settle out, and the water molecules, are going to be separate, that you're going to sit on top, right? So in this case, this is where our molecules, our particles, are actually too big, right? Back to Goldilocks. These particles are so big that they actually fall to the bottom and separate out. So I like this example, and you could start to think about some other examples, maybe where, for example, our maybe vinaigrette. You could open your fridge and maybe you find some salad dressing, and you'll see that, maybe when you bought it, it was mixed up, or before you put it on your salad or whatnot, it looks mixed up. But then over time, right, those heavy particles start to settle out, and then our oil starts to sit on top. So another example of this might be something like ketchup, right? If you go and look in your refrigerator right now, you'll probably see that, a lot of those solid particles of the ketchup start to sit on the bottom. You forget not to shake up that bottle before you go to add it to maybe your hot dog or hamburger, and you end up with that gross kind of like watery ketchup wannabe, right? And it's really gross. But another example of our suspension. So our next term that we want to talk about is a solution. So a solution is homogeneous. It looks the same throughout. And this is, if we go back to Goldilocks, the particles are too small, right? So where a suspension was, the particles were too big, a solution is these particles are too small. And so they uniformly disperse. They completely spread out throughout the substance, no matter how long we let that sit. If you think of like salt water, right? Salt water is basically going to, that salt is never going to settle out. So there's really two parts to a solution, two vocab words that we want you to be aware of. So there's a solute and then a solvent, all right? So our solute, I'll talk about the solute first, is the substance that's dissolved. So it's what we end up adding to the solvent, right? So in this case, this is maybe some copper sulfate when we did that lab that you maybe measured out of the container. And then our solvent is the substance where the solute is dissolved. So this is kind of what does the dissolving. And that's usually present in the largest amount. So in this case, our solvent was water, right? So we take this copper sulfate, we add it to the solvent, which is water, and we make a solution. So thanks to scientists for making those words sound really, really similar, but mean different things. Here you go, quick quiz time. Salt water, all right? So if we have a solution of salt water, what is the solute and what is the solvent? Well, hopefully, based on the last slide, we learned that that solute would be the salt that we're adding, right, to the solvent, which is this glass of water down here. Maybe that's tough to see. So if water's the solvent, and a lot of times it is, water is it's so common that we call it the universal solvent. But when water is that solvent, we call that an aqueous solution. And we symbol that with, when we're talking about states, solid, liquid, gas. If we're making a solution, we would symbolize that an AQ as opposed to maybe the S or the L or G for solid, liquid, gas. So the reason why we call water a universal solvent is because so many substances can dissolve in it, and that's what makes water kind of cool. So those aren't the only types of solutions, solid in a liquid. We could have a gas in a gas solution, such as air. Air's a solution of oxygen, nitrogen, carbon dioxide. We could even have, and here's another vocabulary word for you, a solid in a solid. So some alloys. An alloy is really a solid mixture of two or more metals. So this might be something like steel, like they take carbon and they add it to iron to give it some more strength, or brass or bronze or gold even. We'll talk more about that on the next page. But an alloy, make sure you add that to your notes, is really that mixture of two or more metals. And then you've also, if you go crack a soda, you've seen a gas in a liquid dissolved as a solution. So one of the reasons when we might make an alloy in itself is, a lot of these metals have separate properties that all by themselves are good, but then they also have weaknesses, much like ourselves. And so if we kind of mix and match these different metals, we can kind of get the strengths of both and kind of cover up some of the problems that, say, gold, for example, by itself is really, shiny, really a beautiful metal. However, it's really, really soft. So 24 karat gold, they actually used to tell if it was gold by actually biting into it. It was so soft that it would kind of like make a mold of your teeth when you bit into it. Well, that's not going to be really helpful if we're going to try to wear that as jewelry. If I have that on my ring, on my finger, and I just press it tough against the table, it's going to lose its shape. So, gold, for example, when we talk about carats, you've probably heard that before, is, for example, an alloy of gold that's a mixture with silver and copper to give it some of that hardness, to give it that strength, so it isn't so soft. So our last term that we want to talk about here is a colloid, and this is our Goldilocks. Well, it's not too small, it's not too big, it's just right. So these are intermediate sized particles, or particles that are just medium sized, that are suspended in a liquid, solid, or gas. These are basically stable heterogeneous mixtures. You notice I've kind of shied away from talking about milk this whole time, because milk is a great example where we have a liquid in a liquid colloid. So these particles in here are actually proteins that are actually being suspended in, of course, our universal solvent, water. A couple of other examples that you might be familiar with, if you think about Jello, right? Jello is an example of where we have a gas that's in a solid. Smoke is a solid in a gas. Whipped cream is a gas in a liquid. And then one of my favorites here, fog, is really liquid particles that are that are medium sized and being held kind of in the air. So how do we know the difference between a colloid and a solution, right? In both cases, those particles are being suspended, they're being held up. All right, in the slide with the solutions, I actually had a picture of salt water and a picture of milk side by side. So how do we tell the difference that this one's a solution and this one's a colloid? Well, even if they're clear in appearance, we can use something called, and this is the last thing I'll have you write down, a Tyndall Effect. So the Tyndall Effect is where we actually shine a light through the mixture. And it's kind of cool to see. If we shine a light through what we're unsure of whether it's a solution or a colloid, if we can actually see that light beam, what that tells us is that those particles, those medium-sized particles, are basically deflecting the light in every direction, right? We can actually see that. And this is kind of cool if you want to try this at home. Take maybe just a glass of water with and then put it side by side with maybe just a little bit of milk, and then dilute that with some water. If you have like a laser pointer kind of sitting around, you like to play with the cat or whatever, get that laser pointer, shine it through this glass, and you can actually see, you'll actually see the laser, or in this case, you can actually see that light kind of being reflected in the colloid versus, remember, in the solution, those particles are just too small, right? So the light isn't reflected off of that. So I hope you learned a little bit about solutions. You'll continue to fill out that vocabulary note sheet as we go along in this unit. So if you shouldn't have it completely filled out after watching this, but eventually you will. So continue to work on that as you watch some of these videos. Thanks.